As we saw in the introductory lesson, the essence of logical reasoning is symbolic manipulation. We start with our premises, apply some rules of inference, stringing together these rule applications to form linear proofs. The idea is simple. Getting the details right requires a little care. Let's start with some definitions. A schema is an expression satisfying the grammatical rules of our language, except for the occurrence of metavariables in place of various parts of the expression. For example, the expression shown here is a schema with metavariables phi and psi. A rule of inference is a pattern of reasoning consisting of some schemas, called premises, and one or more additional schemas, called conclusions. Rules of inference are often written as shown here. The schemas above the line are the premises, and the schemas below the line are the conclusions. As we shall see, the meaning of a rule of inference is that we can derive an instance of the conclusion whenever we have corresponding instances of the premises. The rule in this case is called implication elimination because it eliminates the implication from the first premises. It's also sometimes called modus ponens. An instance of a rule of inference is the rule obtained by consistently substituting legal sentences for the metavariables in the rule. For example, the rules on the bottom of the here are both instances of the implication elimination rule. In the first instance, we replace both occurrences of phi by p, and we replace both occurrences of psi by q. In the second instance, we replace both occurrences of phi by p implies q, and we replace both occurrences of psi by q implies r. A rule applies to a set of sentences if and only if there's an instance of the rule in which all of the premises are in that set. In this case, the conclusions of the instance are the results of the rule application. Here's an example. We have a set of 3 sentences to start. Our rule is implication elimination. On the right here, we have an instance of this rule. Both premises are in the set. We have p implies q, and we have p. Consequently, we can derive the result q. Here's another example. In this case, we have the same set of sentences and the same rule, but a different instance. Again, the premises are in our set. We have p implies q implies r. We have p implies q, and so we can derive the conclusion q implies r as a result. Same rule of inference, 2 different results. Note that it's okay to have rules of inference with no premises. Rules with no premises are sometimes called axiom schemata. That's the plural of axiom schema. Axiom schemata are usually written without horizontal lines, like the ones used in ordinary rules of inference. An axiom schema allows us to derive any instance of the schema that we like, without any premises whatsoever. The sentences at the bottom of the slide here are examples. Here are some common axiom schemata. The schema we just saw is called implication creation. The implication distribution axiom schema allows us to distribute one implication over another. If a sentence phi implies that psi implies chi, then if phi implies psi, then phi implies chi. The contradiction realization axiom schema permits us to infer the negation of a sentence if the negation of that sentence implies some sentence and its negation. By stringing together applications of rules of inference, it's possible to derive conclusions that cannot be derived in a single step. The idea of stringing together rule applications leads to the notion of a linear proof. Linear proof of a conclusion from a set of premises is a sequence of sentences terminating in the conclusion, in which each item is either a premise, or an instance of an axiom schema, or the result of applying a rule of inference to earlier items in the sequence. Here's an example. Suppose we have a set of sentences we saw earlier. We start our proof by writing out our premises. We believe p implies q, and we believe that p implies q implies that q implies r. Using implication elimination on the first premise and the second premise, we derive q. Applying implication elimination to the second premise and the third premise, we derive q implies r. Finally, we use the derived premises on lines 4 and 5 to arrive at our desired conclusion. Here's a somewhat more complicated example. This one illustrates the use of axiom schemata. Whenever P is true, Q is true. Whenever Q is true, R is true. With these as premises, we can prove that whenever P is true, R is true. On line 3, we write down an instance of implication creation. Q implies R implies that P implies Q implies R. From this conclusion and premise 2, we use implication elimination to derive the sentence P implies Q implies R. On line 5, we write down an instance of implication distribution. If P implies that Q implies R, then if P implies Q, then P implies R. We combine the conclusions from lines 4 and 5 to derive the sentence on line 6. And finally, we use implication elimination once again to derive the overall conclusion. It's not an easy proof, not a trivial proof, but it works. Later in this lesson, we'll see how to produce a simpler proof of this very same result. This exercise tests your grasp of proofs by asking you to produce a multi-step proof using implication elimination. A collection of rules of inference is called a proof system. Let R be a proof system. If there exists a proof of a sentence phi from a set delta of premises using the rules of inference in R, we say that phi is provable from delta using R. We usually write this as shown here using the provability operator, which is sometimes called a single turnstile. If the set of rules is clear from context, we usually drop this subscript. The Mendelssohn system is a well-known proof system for propositional logic. It consists of the implication rule of inference that we just saw and the 3 axiom schema that we saw. The Mendelssohn system is interesting in that it is sufficient to prove all logical consequences from any set of premises in propositional logic using only the operators not and implication. And as we shall see later, this subset of sentences is interesting because for every sentence in propositional logic, there's a logically equivalent sentence that can be written in terms of these 2 operators. The downside is the proofs in the Mendelssohn system can be a little complicated. The good news is we can eliminate much of this complexity by moving from linear proofs to structured proofs.